This is part 2 of 5 parts of hypothesis testing. Our focus here is on p-values. This is a topic that can be rather confusing, and so that's why we're going to devote an entire segment to this topic. Now, by definition, the p-value is the smallest level of significance at which a given null hypothesis can be rejected. What this means is in a given distribution, if we put the calculated value in that distribution and we look at the area outside of that value, the area under the curve, it's actually the p-value. Now we just talked, in the prior lecture, we're talking about alpha, level of significance. That's the area outside the critical values. The p-value is the area outside the calculated test statistic. So basically, we compare the p-value with the alpha, or the level of significance. So this would be figuring out what the lowest level of alpha must be to reject the null hypothesis, which still doesn't help until you see a diagram, I think. But you calculate the test statistic, and then you have to use a statistical package, a calculator, a spreadsheet to find out the p-value corresponding to that, or the area under the curve. We're not going to actually be calculating the area under the curve using calculus. We're going to rely on other things to help us, other tools. And we're going to figure out what this probability is. And so this is going to be the area outside the calculated value. So we'll look that up in just a moment here. So let's say we have a t-distributed test statistic, and we're testing the null that mu, the population mean, is equal to 5, versus the alternative is that the population mean is not equal to 5. And let's say we have 25 degrees of freedom. We go through all the calculations and we come up with a test statistic of 1.9. So we have to determine what the critical values are, what the p-value is, and how we should make a decision. So let's see how this works. The critical values are plus and minus 2.059539. Now how do we get that? Well, we have several ways to do it. We can use Excel in the TINV function. We can use the TI-83 and use the t-interval function for zero mean, square root of the sample size with standard deviation, and the degrees of freedom plus 1, or 26 for n. If we have a TI-84 or some of the upper models, then we can use the INVT function, where we specify the area to the left of the point, and then that'll give us the same values. Or we can go to Appendix B in the back of the textbook, find the row for 25 degrees of freedom, and the column heading 0.025. So we can get this number many different ways. So here's how it sets up. The critical values, if we get a calculated value that's within the bounds, within plus or minus 2.059539, then we fail to reject. If we get a calculated value outside of this boundary, then we reject the null. Now the p-value corresponding to our calculated value is 0.0684, or 6.84%. And we often put it in percent terms simply because we put alpha in percent, say 5%. We can get the p-value in Excel by using the tdist function, and in the TI-83 we can use it using the tpdf function. So we have two ways of getting this. We specify the calculated value and then the degrees of freedom. Now here's how it works. We compare the p-value with the alpha. If the p-value is lower than the alpha, we reject. If it's higher than the alpha, we fail to reject. And we can see this in a diagram, which I think is the easier way to look at this. We set up the critical values plus or minus 2.06. I've rounded off a little bit just to fit everything in here. Any calculated value between plus or minus 2.06, we will fail to reject the null. Anything outside of the bounds of plus or minus 2.06, we reject the null. So our rejection region is in red and our fail to reject region is in green. Now the calculated value that we did for this statistic is 1.9. That is within the bounds plus or minus 2.06, so we fail to reject. Now if you want to relate this back to the p-value, if you were to draw a line up from that 1.9 and up from negative 1.9 and look at the area outside of that values, then that would be the p-value, which was almost 7%. So it's basically inside the critical values, so we fail to reject. So the p-value is greater than the alpha of 5%. So we reject the null hypothesis. We could have done the same thing by comparing the 1.9 within the critical values plus or minus 2.059539. So we fail to reject the null. So we can get to the same exact conclusion using the p-values or by comparing calculated test statistic with the critical values. We should always get the same decision. So if you look at these examples, and you might want to spend some more time than just flashing through this lecture, but look at this right here, and you have degrees of freedom, you got the alpha, you got the calculated test statistic, which came from some sample we drew, so it's outside of the bounds here. Then we have the critical values, which these are right from the table at the back of your book, Appendix B. And you have the type of test. The critical value depends on the degrees of freedom and how much area is to the right. So in a two-tailed test, the critical values are actually the plus minus 2.042. In the one-tailed test, it's going to be the positive in this case, or in the case of if we had a negative less than alternative, would be the negative of it. But what we do is in the two-tailed test, the alpha has been split between both tables. The Appendix B at the back of your book is set up for focusing on the right side. So if you have an alpha 5%, you look at the column heading 0.025, because that is half of the alpha. Now we can also calculate the p-values using a calculator or Excel, and then we can make our decision. We can make our decision based comparing the calculated t-statistic with the critical, or by comparing the alpha and the p-value. And you can see we get the same exact decision no matter which case we're talking about here. In terms of getting critical values and p-values, you can do this in Excel, where you have the critical values are using the INV function, the p-values are using the DIST functions. And in each case, DF is degrees of freedom. And you can use this in all the different distributions. So there are more distributions than this, but these are the ones that we'll be using. So you might want to try a few of these. Just make sure you can duplicate some of the numbers that you'll see in the lectures, just so you have some comfort level with using the INV functions and the DIST functions. So here's an example. Suppose you have a test in which the calculated t-statistic is 1.98 and there are 32 degrees of freedom. What is the p-value corresponding to the calculated t-value for a two-sided alternative hypothesis? In Excel, we use t-dist, and you'll notice we can use the t-dist function with or without the period between the t and the d. That just has to do with different versions of Excel. I'll give you the same thing. And TI-83 would use the t-pdf function. And we get the same answer. Now, what these are the p-values. Now, in another example, suppose we want to test, have a test in which the calculated chi-square statistic is 45 and there's 30 degrees of freedom. What's the p-value corresponding to this? In this case, we use the DIST function, and we can use the chi-square CDF in our TI-83s, and we get the same, we get a p-value, we get the same p-values. You'll see we had to multiply by 2 because we wanted the area for a two-sided test, and this has to do with how they've been programmed in both Excel and TI-83.